Hello, this presentation will discuss bump mapping. Bump mapping is a method of perturbing surface normals with Phong lighting to give the illusion of small geometric features on the surface. So the idea is you've got a surface modeled with fairly large triangles, say, as a smooth surface, but we want the surface to look like it has small bumps or dents or other small geometric features. And we do this by changing the normals on the surface, on the smooth surface, so the normals are no longer quite correct. But then the Phong lighting, which uses the normals to apply diffuse lighting and specular lighting, makes it look, when we're looking at the surface, as if the surface has those small geometric features. So to write this down, we use a texture map to specify how to perturb normals on a smooth surface so that Phong lighting gives the appearance of small features. So basically the picture is going to be the following. We've got a smooth surface here that's being modeled geometrically. And we've got a perturbed surface, which I'll draw in orange, which has maybe bumps or dents. So this is the perturbed surface, which is the smooth surface changed to be different. So this is a perturbed surface. And then instead of perturbing the surface, which to do that would require lots of little small triangles to pick up all these features, we just look at the normals and we adjust the normals on the smooth surface to match those of the perturbed surface. So just starting here, we're sort of the normals on the smooth surface I'm drawing as red now match actually the slope of the perturbed surface. So right here, where they pass through each other, this is right at right angles. But the normals we think of the normals being based on the smooth surface, but matching the direction of the perturbed surface. So the normals on the smooth surface would look something like this. So I'll get into the mathematics of this in a moment, but first let's take a look at an example on the computer. Here we see a metallic torus with rounded cylinder-shaped bumps textured on using bump mapping. These bumps here are not modeled as part of the geometry. The torus is actually modeled as a series of rectangles in a ray tracing software program, and the normals are perturbed to generate the appearance of bumps. The perturbations of the normals mean the Phong lighting gives you shadow appearances and so on, thus giving the illusion of bumps. But in terms of the geometry, they're not really there at all. The underlying rectangles are pretty large compared to those size of the bumps, certainly much larger than the detail that we see in the bumps. One way to see this is if you look at the silhouette of the torus, like around the right side, around the bottom, you can see the silhouette is completely smooth. There are no bumps sticking out. And this indicates that the bumps are not geometrically present. They're just being rendered there using bump mapping. So now we'll return to the blackboard for some more mathematics. So we want a texture map to specify how the perturbed surface differs from the smooth surface. So the texture map will typically hold well, several things it could hold. It could actually hold the red normals as I've drawn them here. That would be 3 floats per point on the surface. Another thing that's very common to hold is the displacement, the change in the position of the surface needed to form the perturbed surface. So the displacement value would just be a single scalar, a distance. So it would say, I'll draw it here in black here, the displacement would be the distance, d, needed to go from the smooth surface up to the perturbed surface. So this d could be a positive value going upward, d could be a negative value going downward, d could be close to 0 where the two surfaces cross, or it could be exactly equal to 0 where they do cross. So we could just store these d values in the texture map. Another possibility is to store the partial derivatives of the displacement value, because when we do the mathematics on the next board, we'll see that what we really want to know is not the displacement value d, but the partial derivatives of d. Well, let's draw this again. Here's our smooth surface. And I'll assume it's parameterized by a parametric equation, P of uv. So as u and v vary, the parametric equation, or the parametric function P of uv, gives the point on the surface. And I'll have a perturbed surface, which we think of being bumped up and down from the smooth surface. And how does this bumping occur? We're going to follow a displacement value in the direction of the smooth surface. So here's the normals to the smooth surface. So this will be these normals, n of uv. This is the normal to the smooth surface. I've drawn those in green. And then I'll take the displacement value. The displacement of from the smooth surface to the perturbed surface will be some value d times n. So in other words, d is a function of u and v. It's a scalar value. And the perturbed surface, this is the distance of perturbation, or the distance of the displacement, in the direction of the normal n, in the direction of n of uv. So d is a function of u and v. Here, in this right here, d is positive because we're pushing it up in the direction of n. Here, d would be negative because we're pushing the perturbed surface downward. So our new perturbed surface we'll call it P star of uv. Is P of uv plus d of uv times n of uv. And I'm going to stop dropping all these arguments u and v. Just everything now henceforward is a function of u and v. So the P star of uv is the parametric equation of the perturbed surface. So our perturbed normals these were the things I drew in red last time, are going to be in the direction P star, partial of P star with respect to u, cross partial of P star with respect to v, because that's how we can compute normal directions. So we just need formulas for P star of u and P star of v. So the partial of P star with respect to u, well, I'm going to use this formula here. So I've got the partial of P with respect to u, plus, and I use the product rule here, the partial of d with respect to u times n plus d times the partial of n with respect to u. And likewise, the partial of p star with respect to v is partial of p. We need some vector signs here. Partial of p with respect to v plus the partial of d with respect to v times n plus d times the partial of n with respect to v. Now, this is a little bit complicated looking, and we actually make the assumption, we assume, for simplicity, that d is small. So I'll say d is approximately equal to 0, but what I really mean by that is d is not that large. So the displacements are not humongous. The displacements are relatively modest. And also, we assume that partial of n with respect to u and partial of n with respect to v are small, approximately equal to 0. Because we're assuming that the original surface P is fairly smooth, so that means that the normals are changing slowly. So the product of two small things is really small, so we just approximate, so we drop the terms, the final terms, d times partial n with respect to u, and d times partial n with respect to v. So we have that partial of p star with respect to u, we can approximate as partial p partial u plus partial d partial u times n, and partial of p star with respect to v is approximately equal to partial of p with respect to v plus partial of d with respect to v times n. And now, these are our formulas for the partial derivatives, and here's our formulas for the perturbed normals. And this is what is used to generate those red normals that I drew on the previous whiteboard image. So notice that this means the following, that we don't need the partial of n with respect to u or the partial of n with respect to v. Those terms are just dropped. We do need to know the partial of d with respect to u and the partial of d with respect to v, and those can be obtained either by using finite differences. If the texture map contains the values of d, we can approximate the values of the partials of d by taking values of d from adjacent values in the texture map and using finite differences to approximate the partial derivative. On the other hand, another possibility is the texture map could store these partial derivatives of d and storing two values instead of just one, and you could just look up in the texture map to get those values. So that's the basic theory of bump mapping and the end of this presentation. Thank you very much.